All right, good afternoon, morning, everyone. So, welcome to your very first chemistry lesson. So, just to kind of give you guys a little bit of idea of what we're doing today, um, the notes are online, so make sure that you access those. So, this chapter, we're going to thermochemistry. This is a pretty sweet chapter. It does seem like a very long amount of notes, but you'll be fine. So just kind of what I expect of you guys is to type along with whatever we are discussing, and I'll let you guys know exactly what slide goes with what. Another thing I would suggest is instead of pressing enter, typing your answer, because that can kind of mess up your numbering. If you press control return or control enter, just kidding, that gives you a new page. You press shift enter. There you go. You press shift enter or shift return, then it will move you down to the next line and it won't mess up your numbering at all. Okay, so do whatever you guys want to do. These are your notes. Just as a heads up, these are going to be for the grade still, just like normal. So yeah, let's go ahead and get started here. Let me put this, move it up a little bit. Okay. All right, so like I said, we are starting our chapter on thermochemistry. And so what I want you guys to think of is, what are some things that come to mind when you hear the word therm? So maybe, for example, you think of the word thermometer or thermostat, things like that. So when we think of the word therm or thermo, like thermals or whatever, um, it relates to energy, and typically we think of heat. So that's really what this whole chapter is going to be about. So we have numbers 1 through 4 on this slide, 1 all the way through 4. Okay, so first we're going to start off by talking about what energy is. So as I believe we talked about before, energy is the ability to do work. So the reason that I'm able to talk right now and I can sit up and do all this online teaching stuff, which is a little weird because I feel like I'm talking to myself, is because I have energy. So I can't do work without having energy. And it also can supply heat as well. I am currently sitting next to a space heater because I'm kind of cold. So that is releasing a lot of energy, which is helping me to stay warm. The crazy thing though about energy is that it does not have mass or volume. So you can't weigh it in any way. You can't place it into a cylinder and measure how many milliliters it is or anything like that. So the only way that we can measure energy is because of its effect. So for example, temperature change. So the reason it's hot outside is because we are detecting the energy from the sun. We can't measure it in any other way. We can only measure its effects, like temperature. So thermochemistry, what it is exactly, is the study of energy and how that changes during a chemical reaction and during changes in state. So of course, when we go from solid to liquid, then we're going to have energy changing. And same with any chemical reaction, there is either a release or an absorption of energy, which is what we're going to be going over today. So we have numbers 5 through 7 up here. So first thing we're going to talk about is chemical potential energy. And I'm sure you guys have heard of potential energy before. It's the potential to do something. It's like the energy being stored. So it has, I always think of it as like it's potential, it has potential to do work or to release energy or heat or something. So every single substance has some amount of energy inside of it. So every single thing all over, right, has some energy stored inside of it. And so the amount of energy depends on what type of atom it is or how those atoms are arranged. So for example, if we take a look at a bomb versus fireworks, we know that those have very differing amounts of potential energy. A bomb releases far more energy than a firework would. And The reason that is just because the types of atoms, so for example, bombs can use uranium, things like that, while fireworks would use like potassium because it makes it a pretty color. So it's just based on what kind of atom is used and then the arrangement of those atoms. So if you kind of think back, it was a while ago, we were talking about network solids, and we're saying that diamonds like have that really awesome structure that makes them really, really strong, which is why diamonds are so resilient. And so it's really hard to break it apart, right? So that's kind of the same exact idea with this topic here. So it has a lot of energy, or it needs to absorb a lot of energy to be able to break those bonds. So just like a bomb, the more energy it has, the more explosive the breaking of those bonds is going to be. So whenever we have a chemical reaction, basically what's happening is the substance is changing from one substance to another, and hopefully that seems vaguely familiar to you guys. We have talked about that, but of course it all has to deal with potential energy. Some are very easy, it just quickly transfers into another substance easy. Some take a lot more energy, and that's all just based on, like we said before, the kind of atom and the arrangement of those atoms. Okay, so we've got numbers 8 through 10. 8 through 10. So energy, this can occur either as a transfer of heat, or also what we call work, or the combination of both. So the reason that we have these chemical reactions happening is because either heat is changing around, or because those atoms are changing and they're doing work. So we represent this as Q. So heat is Q. So whenever you see Q in an equation or in questions, that's what it's representing. But basically what heat is it's the energy that transfers from one object to another. So a lot of people get heat and temperature kind of mixed up. So temperature is the measurement of heat. So heat is that energy transferring, and temperature is the measure of that. Okay. So if you are increasing heat, then you're adding more energy into something, then that will increase the temperature, which is what we can measure. Going back to that thing of we can't measure energy, but we can measure the effects of it. That's the same thing with heat. So one effect, like mentioned before, if you add heat, it will increase the temperature. If you take away heat, it will decrease the temperature. And so really what the Earth wants, I guess, is to be in equilibrium. So it wants things to be balanced. So heat will flow. So so let's say you have a glass of warm water. You just like left it out in the sun in Las Vegas. It's hot water, and you threw some ice cubes into it. What's going to happen to those ice cubes? Well, the ice cubes are going to melt, right? But what's also going to happen to that water in the glass? The water will also decrease in temperature. So the ice cubes melt, and the water will increase in temperature. So heat flows from a warmer object to a cooler object. This heat is just being exchanged back and forth, until they reach the same temperature and reach that equilibrium, right? So they're going to just go back and forth until they are the same temperature. And so that's exactly what we see whenever we have water or whatever drink with ice, and the ice melts, because they're transferring heat back and forth because they want to be the same temperature. Okay, we have 11 through 13. 11 through 13. Okay, so these chemical reactions, they involve an absorption, so they take in heat or they release heat, or let it go. So how we study these energy changes is something called surroundings and the system. So the system is what you are focusing your attention on. And then the surroundings is everything else surrounding it. So that's really important to remember. The system is what you are focusing your attention on. You're focusing on how the temperature is changing, and the surroundings is everything else around it. Okay? And altogether, this creates something called the universe. Okay, so for example, here we have our glass of water. And let's say, for example, we're going to focus on the ice cube. That is going to be our system. That's what we are focusing on. The surroundings would be everything else. So the air, the cup itself, all of those things would be the surrounding. Okay, so keep that in mind as we move on to the next part, next couple things here. Numbers 14 through 16. So what thermochemistry, like why we care about thermochemistry is because we want to examine how heat is flowing between the system, remember that's what we're focusing on, and its surroundings. So all the things that can influence the system, okay? So a couple chapters ago, we talked about the law of conservation of mass. And in this one, it's the law of conservation of energy. So it's very much the same idea, except instead of talking about mass can either be created or destroyed in a chemical reaction, the law of conservation of energy says that you cannot create or destroy energy either. It's just being recycled. So whenever we have a chemical or a physical process, a chemical reaction, anything like that, the energy of the universe remains unchanged. So you're not creating any energy. Let's say, for example, you set off a firework. You're not releasing all this energy, or you're not creating all this new energy that's being released into the atmosphere that has just, it's already been used. It's just being taken from one place and putting the energy in another place. So the energy we've had at the beginning of the universe is the same amount of energy that we have today. Kind of cool to think about is that the energy I have right now to be talking and moving is just old recycled energy that maybe dinosaurs used to, you know, chase down their prey or whatever. So energy is constantly being recycled, just like mass and just like matter. So I do want to show you guys a quick video of something called Newton's cradle. So if you're not familiar with Newton's cradle, it looks like this image right here. So I'm going to pull this up. So we're going to watch a quick little part of this. So the guy's going to move one ball, it goes back and forth, over and over. And eventually it will lose the energy. But that kind of helps to relate what we're talking to. That things are not being destroyed, they are just being recycled. So as we saw in the Newton's cradle, the energy from one ball gets transferred through to the other ball, and it just keeps going back and forth, and that's the same exact idea whenever we're talking about the law of conservation of energy. It's just being transferred from one thing to another. Okay, we have number 17. Ooh, this is a big slide. 17 through 25. Yeah, that's a big slide. Yeah, very big. Okay, so 17 through 25, here we go. Okay, so remember that system and the surroundings, right? So the system is what we're focusing our attention on. So for example, with the ice in the water, the ice was our system, and the surroundings was like the air, the cup, the things that we're not focusing our attention on, but can still affect our system. Okay, so just remember, keep that in mind. So there's two types of processes that are really important in thermochemistry. One is endothermic, and the other is exothermic. And these words hopefully seem somewhat familiar, maybe from biology. Certain animals are endothermic versus exothermic. Anyway, we'll talk about that in just a second. But if heat is being absorbed into the system, that is what we call an endothermic. So I kind of like to think of endo, it kind of sounds like into. So things are going into something, okay? So heat is being absorbed. It's going into something. So what's happening is that the system is gaining heat, right? So the surroundings is losing heat and the system is gaining heat. So it is literally taking heat from the surroundings and is keeping it for itself. So right now, I am a system. Okay, so we're gonna think of me as the system, and the room around me is the surroundings. So right now, my space heater is losing heat because I, the system, am gaining the heat that it is releasing. So currently, as I'm sitting next to this, I just forgot the word, what the word is, space heater, there we go. As I'm sitting next to the space heater, I am absorbing the heat and it's keeping me warm. So I am currently seeing an endothermic process in action right now. Or if you were to go outside and it's hot, it's in the summer, you are literally, when you're getting hot, you're literally taking heat from the atmosphere and gaining it into your body. It's kind of cool. Okay, so endothermic is going into you. So this is defined as positive Q. So remember, Q means heat. So if there's a positive, it means it is adding heat. So that makes sense. Exothermic is the exact opposite. So I like to think of exothermic. Exo kind of sounds like exit, right? So it is releasing heat into its surroundings. So for example, let's say you're outside and you're running around and you're getting really, really sweaty. And the reason that we sweat is so that it can cool off our body. So if we think of our body as the system and the air around us is the surroundings, as we sweat, we are releasing that heat into the atmosphere. So we are releasing heat into our surroundings. So next time you sweat, you can kind of think of that like, I am releasing heat into the air. I am actually causing the air to get slightly hotter around me because I am releasing heat, okay? So endothermic is heat is going into something. It's being absorbed. Exothermic, heat is being released. It's exiting from the system, okay? So the system's losing heat, the surroundings are gaining heat, and we define this as a negative Q, right? So Q means heat, so negative Q means you are losing heat, which is exactly what we see during an exothermic reaction. Okay, so here are some pictures of an exothermic and an endothermic. So if we look at picture A, this guy is literally doing what I'm doing at this very moment, except instead of a fire, I have a space heater. The surroundings are the fire, the atmosphere around him, and he is the system. And so he is absorbing heat. It is entering him. So this would be an endothermic reaction. Now, if we look at this guy over here, he is a sweaty mess, okay? So he is the system. The surroundings are the air around him. He is releasing heat into the surroundings to help cool him off. So this would be an exothermic reaction, just exiting his body. So hopefully that makes a little bit of sense. I am going to post a video at the end of this, or sorry, post a link with this video that a Tyler DeWitt video that explains this in a little bit more detail, because you know how much I love his videos. He's an awesome chemistry teacher. So let's take a look at this problem here. So it says, on a sunny winter day, the snow on a rooftop begins to melt. As the melted water drips from the roof, it refreezes into icicles. What is the direction of heat flow as the water freezes? Okay, so we're looking at how the heat is moving as the water freezes. So let's think about this for a second. When water is liquid, and it needs to go into a solid, is it going to gain heat? Is it going to get hotter, or is it going to lose heat? Is it going to become colder? So, of course, as it freezes, it is going to lose heat. So the heat flow is leaving the water and it's going into the atmosphere. So the water is the system, the surroundings is the atmosphere, everything else around it. So it is leaving, so it is exiting, right? So this would be an exothermic reaction because the heat is being released. It is leaving the system and going into the surroundings. Okay, so let's take a look at number 26 in your notes. It says a container of melted wax stands at room temperature. What is the direction of heat flow as the liquid wax solidifies? So I do want you to think about that for just a second. But so the wax is going from a liquid into a solid. So that sounds kind of similar to the sample problem we just did, right? So if the heat is leaving the wax, and if our wax is the system, then what do you think that would be? So the heat is leaving the wax. What type of reaction would that be? Hopefully you thought it was exothermic, because it is, okay, because the heat is exiting the wax and going away, right? Because it is losing heat, it's cooling off, it's solidifying. If we look at 27, it says a cup of cold water is left out in the sun. The ice all melts. What is the direction of heat flow as the ice melts? So we got to think of this, the ice melting. So is the ice gaining or is it losing heat? Well, for ice to melt, it needs to gain heat, right? Because it needs to warm up to melt. So the ice is absorbing the light or the energy from the sun. So if ice is our system and the outside is our surroundings, then the ice is absorbing the heat, right? So if it's absorbing or entering, or the energy is entering into the ice, what type of reaction would that be? Hopefully you thought it was endothermic because it is. Okay, so like I said, if you're still not totally sure about the difference between endo and endothermic and exothermic, I'm going to post a video by Tyler DeWitt as well, and he does a really, really great job of explaining the difference between the endo and exothermic. Okay, we are going to keep going. I know this is a lot of notes. I've been talking forever, but it's fine. Okay, we're almost done. We've got numbers 28 through 31. 28 through 31. Okay, so the last thing we're going to talk about is this thing called heat capacity. And it sounds kind of like a new word, but trust me when I say it's something that you are very familiar with. You just might not have known the vocabulary that went with it. So let's say you have an object and you want to increase the temperature of it exactly 1 degree. Why? Why not, right? So you want to increase the temperature 1 degree Celsius. That is what we call the heat capacity. So if we break apart the word heat, right? Heat, we just talked about that capacity. So that's the amount of heat needed to increase the temperature. So there are a couple things that can affect the heat capacity of an object. It depends on its mass. So the bigger the object is, the more heat it's going to need to change, and also its chemical composition, which we'll see in the next slide. So of course, let's say for example, how many of you guys have ever gone to your car and you accidentally touch like the buckle of your seatbelt and it hurts like really bad, right? It's very hot, okay? So for that metal, it's a small piece of metal, right? So it's going to heat up a lot quicker than, let's say, for example, I don't know, a bridge, okay? That's also made out of metal. You don't touch the bridge and go, oh my gosh, I burned myself, right? It needs a lot more energy, it needs a lot more heat to warm up than your seatbelt buckle would. So sometimes, so of course, the mass of the object can affect it, but also the composition, right? So let's say, for example, you have a puddle of water, you stick your little toe in it, and it's cool. Water takes a while to heat up, and if you've ever boiled water, you probably have noticed this. But let's say, for example, there is an iron sewer cover. First of all, stinky. But if you were to touch it and it's like out in the hot sun in Las Vegas, it's going to get hot pretty fast. So why are we seeing that a puddle of water the same size as the sewer cover, why are they not heating up at the same time? Well, that's because of their heat capacity. So if we are to look at this, let me move my face here. If we were to look at this chart here, and by the way, we've got numbers 32 and 33 on this slide. This all relates to something called specific heat. So what specific heat is it's the amount, or the substance, sorry, is the amount of heat it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. So let's say you take chloroform, that's fun, pass some people out, I guess. You take a gram of chloroform and you want to boil, or you want to raise it 1 degree because, hey, you have extra chloroform laying around, whatever. So you would need 0.96 joules, that's what J is, joules per gram to increase it 1 degree Celsius. That's kind of a lot of words. Basically what the moral of the story is that the higher the number, the more energy it needs to increase its temperature. So for example, water takes 4.18 joules. That's a lot of energy. And you've probably noticed that, like I mentioned earlier, if you boil water, it takes a while. It doesn't happen that fast. While if you try to, I mean, think about mercury. It's liquid at room temperature. It's the only metal that is liquid at room temperature. It has a very, very low specific heat. So if you wanted to change its state from solid, liquid, gas, it's very, very easy. While liquid water takes a lot more energy. And we'll go more into this in a couple more chapters, but that's kind of what's going on right there. So the higher the number, the more heat, more energy it takes. The lower the number, the less energy it's going to need to be able to change its temperature. Okay, we got our last slide here. Here we go. Actually, I'm going to leave it down there. Okay, we've got number 34. Oh, and by the way, sorry, number 33. So the one that has the highest specific heat, the highest number, is liquid water. Hopefully you noticed that. And the lowest is mercury. So hopefully you got those two. Good to go. So how many of you guys have ever been to California? I bet a lot of you, right? So I grew up in LA, North LA, and we never really experienced very large swings of temperature like we do in Las Vegas, or when I lived in Idaho, I would literally experience a 100-degree Fahrenheit temperature difference between winter and summer. So in California, you don't really have that, and there's a reason for that, and that's because of this heat capacity. So just like it takes a lot of heat to raise the temperature of water, water also releases a lot of heat as it cools. So if you live by a lake or an ocean, it releases that heat it absorbed back into the air when nighttime comes. So this is why areas that are by the coast have more moderate climates. So if we look at this image of California here, San Diego, highs of 74 and a low of 66. That's like a change of 8 degrees. That is not much of a difference. Los Angeles, we have a little bit more, but it's still really not that crazy. San Francisco, a change of 20 degrees. But if we looked at like Tahoe Valley, that's a change of 40 degrees between night and day. Death Valley, another 40 degrees. we see quite a change in temperature in the more coast, what's the word I'm thinking of? Interstate locations. We see more of a change of temperature than right along the coast, and that's because of heat capacity. So make sure you guys get all those notes done. I know this was a lot. I have some cool demos I'm going to show you guys the next 2 days. So just make sure you're staying on top of everything and have a great day.